person. So today the topic of my talk is about gravitational waves. Let me start just by just a brief introduction. Gravitational waves are perturbations on the space-time curvature. So here, for example, you can see you have a background space-time curvature, which is like the surface of this orange, and then you have the little ripples here, which corresponds to smaller scale perturbations, which corresponds to gravitational waves. So these waves can be emitted by oscillating matter, and they propagate at the speed of light according to relativity. And then the leading order emission is quadruple radiation. And then the gravitational wave causes changes in relative positions of free test masses. And the amplitude of the wave basically corresponds to the strain it induces in between objects. So there's a long history of gravitational wave detection, just like Professor Hall was talking about. Every field, it takes a long time to develop. But I think right now is also a very good time to enter gravitational wave research. So basically, the detection started in the 60s with Joe Weber. And he was using resonant mass detectors. Later on, Ray Wise and others proposed to use microsync interferometers to detect gravitational waves. And they soon realized that you need 4-kilometer sized microsync interferometers to actually reach sensitivities that will be meaningful for detecting astrophysical gravitational waves. So, in this picture, I'm showing the LIGO detectors, and then these are 4-kilometer interferometers that started operating 20 years ago in 2000. And then actually the first science run for the LIGO detectors was when I was a graduate student, around 2003, I think. But it was a second generation of detectors that actually made the first detection in 2015. But then in the past 5 or so years, we have detected around 100 pairs of merging black holes, one neutron star binary merger that also induced electromagnetic counterparts. There were a few more detections which involved neutron stars, but no electromagnetic counterpart was detected. So the detection in principle is very simple. It's a microsync interferometer where light comes in, measures the differential arm length change induced by the gravitational waves. And then it's the very good sensitivity here, which really these detectors are able to right now measure a strain of 10 to the minus 23. Okay, so this is really the sensitivity that enabled the detection of gravitational waves. So in my talk today, I will mainly talk about using gravitational waves to study black holes, like a little bit related to the previous talk, and how you would demonstrate and test predictions of general relativity in the context of black holes. And also, looking more toward the future, what kind of physics you might, or exotic physics you might look for, and using gravitational waves for studying the evolution of the universe and large scale structures. Towards the end of the talk, I would also talk, a little bit about, what the fact that we have such a good sensitivity on measuring positions of test masses. These are in the regime of quantum metrology. It turns out that we can use LIGO technology to study the quantum mechanical behaviors of macroscopic objects. Even in some cases, maybe speculative, but looking for the validity of quantum mechanics, whether there are violations or whether there are new effects when quantum mechanics and gravity are involved in this regime. So let me first briefly introduce one of the major kind of waves that we look for in LIGO. These are the mergers of black holes. At the beginning, these two black holes, they circle around each other, but then due to the radiation of gravitational waves, they lose energy, and then their orbit gets closer and closer. And then the amplitude of the wave would increase, and then the frequency of the wave would increase up till the moment when the two black holes will touch. And then they go through the merger stage where they merge into a final black hole. And the final black hole will ring and then give you a so-called ring-down wave. I will go into more details later in the talk. Here, the more the point is the time scale. So basically, this illustrates the first detection. The two black holes are around 30 solar masses. And then the frequency at which they emit these waves are like around 200 some hertz, up to 200 hertz. And then the lowest frequency that we were able to catch these waves here are around 40 or 50 hertz. So this is in this acoustic frequency band that we're detecting these stellar mass black hole binaries. So this is the first event that we detected. And the first binary neutron star event was also very exciting. It turned out to be, it triggered a lot of astronomical interests in 2017. And then there was this event, 170817, so-called, and that was a merger of binary neutron stars, which triggered gamma ray burst, and also a lot of other emissions in the visible and other frequency bands. So this first detection of neutron star binaries also was observed in the, somehow I can't point. That's okay. Sorry. Maybe I should do this. This way I can point, I think. So basically, so this was also observed, in the different frequency bands of the electromagnetic spectrum. And this triggered a lot of interest, which revealed a lot about, what happens after the neutron stars merge. There are matter that are ejected, and then these matter then will go through nuclear reactions that produce heavy elements. Okay, so it's a very interesting process for observational astrophysics. So after the first detection, there was a few science observation runs of LIGO, since then, in the so-called 01 and 02 runs, which were like, the dates are shown here. Basically, I think it was more like a year of observation. We detected 10 binary black holes in total. And then the more recent release of data and the release of results was from the first part of the so-called 03 run. So the 03 is the third observation run, which was from the April of 2019 to the April of 2020. So in this event, and then in the first half of the 03 run, the data was released, and also there were 39 events that were released from this catalog. And among these, as you can see here, most of the events are binary black holes. Some of them are possibly binary neutron stars, and some of them are possibly neutron star black hole binaries. It actually requires a lot more sensitivity for us to really say whether these are, either binary neutron stars, binary black holes, or neutron star black hole binaries. So you can refer to these two papers for details. So from this, the immediate information you get are the distributions of masses of these individual black holes. Shown in these columns here are the mass of the primary black hole, which is the heavier one, and also the mass ratio. And also the chi effective here describes the effective spin parameter that measures how fast these are spinning. So predominantly the conclusion seems to be that these black holes are heavier than what we had thought before. I think maybe the more of them are 30, 40, even, there were like, even one pair of binary was more approaching, the total mass is more like 150 solar masses. These are really heavier than what astrophysicists were predicting before. And also, it turns out the spins of the individual black holes, most of them are pretty low, which was also a little bit surprising. But later on, Jim Fuller et al. They explained the low spin due to processes that are during the birth of these black holes during the collapse process. The magnetic field can transfer angular momentum out, and therefore maybe it is natural to form black holes from collapse, which are slowly spinning. So these are the kind of more like the population kind of information. There were also tests of relativity that are performed on these waveforms. So let me first briefly review several very standard tests. And then in the second part of my talk, I will talk more about some different physical theories that can be tested. Okay. So here in the first kind of test is a consistency test. So what you do is you break your wave into two pieces. The early part, in the upper left figure, you have early part of the wave and late part of the wave. And what you do is you actually you use theoretical templates to see what are the parameters that corresponds to the early part of the wave, and then you predict a final mass and final spin for the remnant black hole, the product of the merger, from the early part. And then you take your theoretical model, and then we measure the final mass and final spin from the second part of the wave. And we look for a consistency between these two tests, these two measurements, and we see whether they're consistent. I think the motivation behind this was that, if during the merger process, there is missing energy or missing angular momentum due to some additional physics, you measure frequency between these two parts of the waveform. But we did not actually see inconsistency. So this is basically saying that within the statistical accuracy of our detectors, the early and the late part of the waveforms are consistent. Another test, is going into more the so-called post-Newtonian expansion of the gravitational waveforms. So basically, you first say that let's parameterize write down our waveform. Okay, I really should, let me point this way. So you write down your waveform as an amplitude and phase as functions of frequency. And then you say that, okay, from theoretical modeling, I know how the amplitude should depend on frequency and how the phase should depend on frequency from numerical relativity simulations, which directly solve the Einstein's equations. And then we nevertheless write down the waveform as an expansion in terms of f to the some integer over 3. Okay, so this power law expansion corresponds to a 1 over r expansion or v over c expansion, in the perturbative regime. So therefore, we have these coefficients which are supposed to be from numerical simulations, from actual theoretical modeling. And then we also measure these coefficients from the binary waveforms. And we look for discrepancy of the phase, especially the phase evolution of the binary that follow particular power laws. Okay, and these are basically looking for, it's a parameterized test looking for generic discrepancies from theoretical predictions. And this is not, there was no discrepancy, no significant discrepancy. Okay, and then finally, there's another parameterized test, which is regarding the propagation of gravitational wave through the universe. So here we were assuming that the gravitational wave at the particular frequencies would gain a particular phase shift in a particular power law. Okay, this corresponds to a modified dispersion relation. And then these different power laws, for different values of the power law, we can constrain the coefficient in front of these modifications. And basically, we have also seen that here in the data, from the data, there is no systematic discrepancy of the dispersion of the waves within our statistical uncertainty. So basically from these tests, we're saying that we have measured, not only measured 100 or roughly an order of 100 binary black hole waveforms. They really seem to agree with the predictions of relativity, both in the generation of the waves and in the propagation. Okay, so this is the current status. We will continue into the future with gradually increased sensitivity, but we will also upgrade our facilities, upgrade our instruments within the LIGO facility, and also in Europe and in the US, we're proposing to have more sensitive detectors, ground-based detectors. So these are basically going to propose to increase our sensitivity by factors of, a few, 3 or 4, on the ground, and then up to a factor of 20 or 30 if we have new facilities. So I will mention a little bit more why we want to have these new capabilities. Okay. So not only on the ground, there's also proposed space-based gravitational wave detectors. So as I mentioned, on the ground, we're looking for gravitational waves that are, from the several tens of hertz up to kilohertz. But in space, we will be able to probe gravitational waves that are in the millihertz band. So these will really target very low frequency gravitational waves that will be emitted by supermassive black holes merging, or by smaller stellar mass black holes plunging into supermassive black holes. So these projects were conceived in the 1990s, or maybe even earlier, okay? And then the current plan by the European Space Agency is to launch the LISA project in around 2034. And the LISA project is, interferometer that circles the sun, and the arm length is 2.5 million kilometers. There's also, proposed by Chinese scientists, the Taiji and the Tianqin projects. These are, the Taiji project is very similar on the left. It's very similar to the LISA project. I think it's kind of taking LISA as a model and to model after that, It's led by by various institutes in the Chinese Academy. The planned sensitivity is very similar to LISA, but I think the idea is that I think it's a very interesting opportunity for research, is that if there are 2 space-based gravitational wave detectors in space, what will be some of the new science you're able to perform, in presence of both detectors in space. And the other thing is the Tianqin project, and it's a little bit different. It's proposed by Professor Luo Jun from the Sun Yat-sen University, also from Huazhong University of Science and Technology. Here, it's more like a Earth geocentric orbit. And here, the Tianqin project may have a slightly higher band of sensitivity than LISA and Taiji. So these are the space-based detectors. Not only will allow us to look for supermassive black holes, it also actually allows us to observe some of the white dwarf binaries. And actually observing white dwarf binaries may have consequences for understanding type 1a supernova potentially. So therefore, in the future, not only will we have improved sensitivities on the ground, we will have space-based detectors in the middle. And also, as I haven't mentioned before, there's a so-called pulsar timing approach for detecting gravitational waves that would even go lower frequencies. And these approaches measuring arrival times of pulses from pulsars. And these may be affected by gravitational wave that pass by, and therefore by monitoring very stable pulsars, this is a way to observe very low frequency gravitational waves. So one thing I want to mention is, if you think about the kind of black holes, these detectors, let's just talk about the ground-based and the space-based laser interferometers. They will be probing black holes with different masses. Also, I think the important thing is to see that they can actually probe to a very large distance into the universe. So in this diagram, so this shows that, okay, the LISA project is able to probe very heavy black holes, including the 10 to the 6 solar mass black holes, which are comparable in mass to the Milky Way black holes. And these ones are believed to be at the centers of galaxies. And then if you look at the redshift they're reaching, well, basically they're reaching such high redshifts where maybe the first galaxies have not formed, or maybe, therefore the idea would be that they would really probe all the binaries that are merging, whose retarded time is within our observation time. Okay, so therefore it's very dramatic. And if you look at the Cosmic Explorer and the Einstein telescope in this plots, you will see that they also, for the 100 solar mass or 1,000 solar mass kind of black holes, or tens of solar mass black holes, they would also reach regimes which are kind of like the distance where we really think the first galaxies have formed. So in some sense, we can say that the reason why we want to build these capabilities on the ground and in space is that we will really want to reach all the binary black hole mergers that happen in the universe. Okay, so maybe by the 2030, 35 or something, when all the detectors, maybe it'll be 2040. Maybe by the time we build these detectors, we will see something different as well. Maybe we'll find out, oh, there's actually a lot more black holes at high redshift, which may lead to even higher redshift sources. That we don't know. But right now, I think we're really planning to be able to see all the binaries that would merge in the universe. I think this is really a very strong statement. And therefore, not only will we be able to probe the formation history, the population, but also very importantly, we can correlate the locations of these binaries that we have seen, including how far they are and where they are, and correlate them with the other indicators of large-scale structures of the universe. And this way, we will also have not only a tool for studying the evolution of the universe, but also the growth of structure or of the universe. Okay, so this is talking about the improved sensitivity. But let me then come back to testing relativity and testing black hole physics. So what are some of the things that we think we are going to be able to do theoretically with probing black holes, probing relativity? So one thing is, there are modified theories of gravity, for example, adding terms into the action, into the Einstein-Hilbert action, which are motivated by theories of quantum gravity. So certainly these are, maybe you might debate on, what is the scale at which they would appear. It's not clear, but on the other hand, these are basically terms you can add into the action anyway, and then you can predict what their consequences are, and you systematically search for deviations from the Einstein-Hilbert action. So one example is the so-called Chern-Simons gravity, which I have listed here. So it turns out it's a very interesting technical problem for people who are interested in learning about relativity, because it turns out, if you add this higher derivative term, these higher quadratic terms in Riemann tensor, you actually get higher derivative terms in your equations of motion, and then you may not have well-posed initial value problems. So I think from the EFT point of view, you may say, yeah, these are perturbative terms, which maybe are not supposed to become the dominant contributions in your calculation, and therefore they should be treated perturbatively. On the other hand, if you have a merging binary black hole, you don't want to be completely doing perturbation theory, because even in general relativity, you have nonlinearities within the R term. So I think one very exciting development in the past few years was by these approach where you first numerically solve Einstein's equations for binary black holes, and you use your numerical simulation as a background, and then you evolve the theta scalar field, and you evolve metric perturbations according to a new set of perturbative laws that uses the Chern-Simons parameter as a small parameter. Okay, so in this way, you basically evolve perturbations on top of a non-linearly obtained full numerical spacetime, and then you can obtain the corrections to the GR waveforms when the Chern-Simons correction is weak. So this is about thinking about a theory which are modifications of GR. So there are interesting features within relativity which are also interesting. For example, the so-called gravitational memory effect. So from the GR point of view, the idea is that if you have a free masses, and then if you have gravitational wave pass through the free masses, you will find out that after the wave will pass through them, maybe the free masses, they will have a new configuration which is different from the old configuration, like this one, okay? So this had various ways of thinking about it, various levels of rigor and sophistication. So you can read it, Christodoulou in the 1990s connected this effect to a very general nonlinear feature of the general relativity. And then later on, these kind of memory effects was connected to the soft graviton theorem, and then also related to the information content of gravitational field. So therefore, this memory effect is has a very interesting theoretical kind of origin. So in gravitational waves, how does the memory effect show up? It'll basically mean that if you look at this train of gravitational waves, if you look very carefully at the end of the wave, it goes up like this. Basically, the strain, gravitational wave strain, would have some kind of non-oscillatory component, which will actually gradually increase and stay at a constant. Of course, the LIGO detectors won't be held at the constant displacement because these pendulums have restoring forces. But what you're supposed to see is that this ramp up actually will be detectable by the detectors. And it turns out that our sensitivity right now is not enough to detect a single memory effect from a single event. But if we stack together multiple events, it is possible to look for such a shift in the strain before and after the merger part of the wave. So this is about testing, this is about demonstrating an interesting feature in relativity. Let me give you another example about studying the horizon of the black holes. Okay, this is a little bit connectable to the previous talk. I think the immediate thing you want to ask is, now we have the so-called ringdown part. Is it an oscillation of the black hole, or in what sense is it an oscillation of the black hole? As it turns out, depending on your definition of what a black hole is, it's usually not an oscillation of the black hole, because the ringdown part of the gravitational wave is due to gravitational wave packets which are circulating the final black hole on the circular orbits, which are precessing and circling the final black hole. This is connectable to a WKB treatment of wave equations in the background, curved spacetime. So basically, the idea is that if you see the quasi-normal mode ringing of the black hole, the ring down of the black hole, you have not detected the horizon, but you have detected the photosphere around the black hole, where null rays are circling the black hole on circular orbits. So then what about the horizon? We want to see the horizon, okay? So the horizon on its own, I think by definition from Stephen Hawking, would be that the event horizon is a location which separates the region where you're able to reach the black hole, where you're able to reach infinity, and the region you cannot. So therefore, if you think about it, the horizon, by definition, is something that you cannot see. But of course, if you have any structure which are a little bit outside the horizon, maybe then they can reflect waves and make the black hole not black. And I think that would be one way you can say, or at least my point of view of looking for these so-called echoes. Okay, so these echoes triggered a lot of interest in the past few years. And these authors claimed, probably wrongly, that they have seen these echoes after the main gravitational waves from LIGO events. So, and their explanation is that actually, if you have some signal, some gravitational wave that propagates around towards the final horizon, if you have some barrier, if the black hole is not a true black hole, but have some kind of surface corrections near the horizon, maybe these waves can be reflected from that barrier. But then these waves that are reflected, they actually get turned back by the photosphere of the black hole, and some of them will pass through the photosphere. So one way to think about it is to say that, yeah, the gravitational wave packet that gets reflected from the barrier, they try to escape the black hole, but a lot of them cannot escape because they're not propagating along directly the radial direction. So they get turned back, and they go back to the barrier again, and maybe they can get reflected again and again. So therefore, if you generically speaking, if you have some structures right outside the horizon, what you would expect is that if you send in gravitational waves toward the black hole, the waves may travel back and forth between this barrier, which are outside the horizon, and the photosphere, and then cause these echoes. So one way to think about is to see this space-time diagram, where I have this red line is a particle that falls down the black hole, and then together with the particle, it carries a gravitational wave packet. And then, if you actually take the packet, the particle triggers a packet right outside the black hole on the photosphere. It triggers a packet of gravitational waves that circles the photosphere, and that will give you the Ringdown wave. But some of these waves that propagate towards the horizon, they may get reflected by the barrier and then come out as an echo, or they may be reflected again and give you another echo. And therefore, this is a more detailed way to explain how the gravitational wave in the Ringdown is generated and how the echoes might actually form. So why are we so intrigued by the echo? I think one reason is just like, it's not numerology, but it's a little bit like that. So if you think about the location at which the waves might be reflected from the horizon, and then you can say, oh, what about a proper distance delta away from the horizon? What you find out is that if you reflect a wave from a proper distance delta from the horizon, it'll lead to the echoes, which are separated by 2 over kappa times a log of delta over the m. Okay, so the kappa is the surface gravity of the black hole, which is of the order of the mass. Okay, so or 1 over, yeah, maybe 1 over the mass. Maybe I got it wrong. No, it's 1 over the mass. 1 over the mass. Okay, therefore at the end, this thing is the mass of the black hole times the log of the proper distance of the reflecting location divided by the mass of the black hole. So what does it mean? It means the log is very intriguing, right? So this log is very important in various aspects of black hole physics, right? If you ask Hawking radiation and unruly effects, it's all relatable by the fact that, when you go close to the horizon, you have this logarithmic behavior. So therefore, it means that even if I want to have a Planck distance away from the horizon, the time difference between echoes is only 14 milliseconds. Okay, and the longer than 14 milliseconds means your distance is less than the Planck distance. So therefore, this really means that if you believe in echoes, it means that you're able to probe structures which are really Planck scale above the horizon, whatever that means. Okay, Planck scale above the horizon. So this is the intriguing side, which is the good intriguing side. But of course, immediately you find out that if you believe in the classical physics of general relativity and the classical black hole physics, such reflection of energy from a distance Planck distance away from the black hole is just such not going to be possible. Okay, so the one way to think about it is to say, okay, I have these gravitational waves, which are propagating into the extreme compact object. Okay, suppose this is a so-called tortoise coordinate system. So basically, the idea is that when your echoes are being reprocessed and then launched back to infinity, what happens is all of the energy content of your echoes are going to be squeezed within a region which is Planck distance away from the black hole. But the problem, of course, is that if you believe in the hoop conjecture or anything about black holes, if you stuff this much energy into a region this small, the whole thing will just collapse. And its collapse is not because the energy hits the black hole and makes it collapse. It collapses because the energy content of the wave gravitates and prevents anything from escaping, okay? So it means that you cannot literally understand the echo from extreme compact objects as if literally there's a compact object which reflects waves. What really happens is that there's some mysterious non-local physics which are outside the horizon, which will make gravitational waves get reflected. So therefore, it shows that we can use this to test for black hole physics, but keeping in mind that it's very dramatic modifications of physics near the horizon that will give rise to these effects. Okay, so let me finally say that the other very interesting aspect of gravitational wave detection is also in the search of dark matter in this very specific way, where we know that for Kerr black holes, any massive scalar field or massive fields outside the Kerr black hole actually is unstable, in the sense that if you have the Compton wavelength of the particle comparable to a Kerr black hole, you will have the Penrose process, it's the Nobel Prize winner. So as a Penrose process, basically it means that the energy of the rotation of the black hole is extracted, and in this case, in the form of a heightened amplitude of the scalar field. And basically, if you have massive scalar fields like the axion, therefore they can be generated from these Kerr black holes, which are right, after the merger of two black holes. And then there are proposals to search for these gravitational waves, and there are ongoing searches for such gravitational wave signatures from LIGO data. So let me just, okay, since the time is getting to the very close to the end, let me just very briefly jump into the other topic, which I also want to mention just for a little bit, which is that the detectors allow us to study relativity, but it also allows us to study quantum mechanics. Because the sensitivity of these devices are actually so good that they are really near, in some sense, near the limit posed to us by the Heisenberg uncertainty principle when you apply that to 40 kilogram test masses. Basically, so here, it's a kind of like a so-called concept called the standard quantum limit. So the concept comes from the fact that if you measure the mass of a mirror, you will perturb its momentum because of the Heisenberg uncertainty principle. And then when you perturb the momentum, it'll cause a additional motion, and that motion would cause noise in your future measurements. So this kind of argument has led to the so-called standard quantum limit, which for LIGO poses a certain limitation of sensitivity. And this limitation is actually not far beyond our current sensitivity. This, as it turns out, this kind of limit can be surpassed by establishing quantum correlations between light and masses. So the theory of this has been proposed in the past 20 years, I guess, but it's only more recently that experimentalists in LIGO have achieved such a situation. Okay, so here I'm going to briefly show this noise curve. So basically here, these two, I think this curve shows the actual total noise that currently LIGO measures, and the quantum mechanical contribution from just quantum fluctuations would be this blue curve. And then when squeezed vacuum is injected in the appropriate way, the noise, the total noise is lowered in this region, just a tiny little bit in this region. But if you extract the quantum contribution of that, it actually corresponds to this curve. And this curve actually is quite below the blue curve. And it's also below the so-called standard quantum limit. So what it means is that even though our classical thermal fluctuations and other noise is still kind of high by a factor of a few, 2 maybe, it does demonstrate that if you inject quantum correlations into the detector, the masses are able to respond in such a way that the quantum noise of the detector is below this naive standard quantum limit set forth by using the Heisenberg uncertainty principle. So it does mean that the delta x times delta p of the test mass is not far below, not far above the h bar over 2. So it means that these macroscopic masses are actually moving in the quantum regime. So people have thought about ways of doing this, ways of using this fact that whether you can, what can you do? Certainly you can think about ways to say that we can prepare quantum mechanical states for these macroscopic objects which have no classical counterparts. And then, there were a lot of recent interests in answering the question, or maybe addressing the question of, using considering using gravity to transfer quantum entanglement, and therefore explore the interface between quantum mechanics and gravity in precision measurements experiments. I think this is maybe LIGO is not the best way to do it, but the related technology in so-called optomechanical systems, it will be one interesting way to probe these questions experimentally. So let me end my talk by showing the summary slide again. I think using the gravitational wave data, we not only measure the populations, not only speculating, but actually explaining the origins of these binaries, how they have formed. And then we will move on to more demonstrations and tests of non-trivial effects in relativity, and putting bound on alternative theories. If we don't see the echoes, and then we will bound how black the black holes can be, and also, correlating with large-scale structures, trying to, understand large-scale structures of the universe. And finally, the quantum technology in LIGO is at the frontier of, understanding macroscopic quantum mechanics. Thank you.
Any questions?
I saw one question on the Q&A. Should I answer the question on the angle between LISA detector orbital plane and the detector plane and the orbital plane is 60 degrees? Is there a reason for that? I can answer this question. I think this is understood as a very stable orbit because, as it turns out, if you put three things, the three things are actually each following a heliocentric orbit in such a way tilted so that it appears that they have this triangular formation around the sun. So if you only have the sun, if there's no Earth and no other planets, this triangular orbit configuration, which is tilted 60 degrees away from the plane of the orbit, is the stable configuration. And if you use any other angles, it won't be stable. I think that's the reason. But of course, now we have perturbations from the Earth and from other things. Then there are more detailed calculations of the orbit that will make sure that the orbit does not deform too much during the mission time.
Any more questions?
So, LIGO have any
you mentioned the squeeze talking down below the standard probability. LIGO any friend in O4 with that?
Sorry, I can't hear the question very clearly. Either use the microphone or the.
Yeah, sorry. I just wondering when did the brain of the LIGO logo adopt this squeeze bucking to reduce noise to the beyond the standard probability?
Oh, sorry, I still can't hear. It's about the squeeze vacuum, right?
Yes, and I was wondering when did the LIGO plan to adopt this scheme and make it work?
Oh, I think right now the LIGO's plan is to upgrade to A+, which is using the so-called filter cavity. Okay, so this is I think right now the squeezing can already improve LIGO sensitivity, but there's a planned A+ upgrade, which will install a so-called filter cavity here in between the squeezer and the interferometer, so that when you use the squeezing, the phase squeezing here would improve the sensitivity without having the anti-squeezing of the amplitude here jeopardize your low frequency sensitivity. I don't know exactly the plan of the A+ upgrade, but I think it will certainly be done. And that will be before this will be before the so-called Voyager upgrade, which is a more ambitious one with cryogenic systems and higher laser power. So A+ has already been planned and will happen. I think right now I don't exactly know the schedule though.
Okay.
Can you hear me?
Yes.
So thanks for the nice talk. Is it convenient for me to get you to get to the slide where you showed the action for dynamical Chen-Simons theory?
Oh, the Chen-Simons. Yeah. Okay. Yes.
Hey, thanks. So the chair of this conference isn't here today, but I just want to briefly comment that some time ago, together with other collaborators, he found a solution where the background isn't just GR, so he turned on a free scalar field for data, which can be interpreted as the axiom. And they studied gravitational perturbations about this background. And they found gravitational wave solutions, which are interesting in the sense that the left circularly polarized wave and the right polarized waves travel with different dispersion relations. So that's the well-known birefringence effect. So I was just curious whether, in this case, you mentioned that you use GR solution as the background, and supposedly you turn off the data field. Do you get something that is similar?
Yes, I think so. So you will have a birefringence. I think the most interesting birefringence effect is or easy to explain one, is the so-called ringdown process. So in the ringdown of black holes, usually there's a feature called the isospectrality. Okay, isospectrality means that the electric type quasi-normal mode and the magnetic type quasi-normal mode have the same set of eigenfrequencies. So this is very unusual for a microwave system or for any other resonant systems. Because, for example, in microwave cavities, the TE and TM modes have very different spectra, usually. And the magnetic dipole, electric dipole, magnetic dipole, quadrupole, all the radiations are not supposed to, generically speaking, have the same eigenfrequency. But for black holes in general relativity, they have the magnetic type and electric type ringdowns originally have the same set of eigenfrequencies. But in the Chen-Simons case, there's a break of that isospectrality. So basically the ringdown spectrum is different for electric type and magnetic type ringdowns. And they are basically different polarization states of the ringdown wave. So therefore, this is like a birefringence for gravitational waves propagating near a black hole. I think this is one example. Another example, I think, is in the Chern-Simons theory. When you apply the Chern-Simons theory to the universe, I think actually just the propagation of the gravitational wave actually has a natural birefringence. When you consider an expanding universe, and then I think actually different polarizations of the wave are already propagating at different speeds. So therefore, there is a birefringence as well. But personally here, in the more relevant to the slide here is this ringdown process have a split split spectrum. I think that corresponds to the birefringence here in the strong field regime.
Thanks.
Here I have a question. On theory side, there are quite a number of studies of symmetry breaking, like yet-to-weak phase transition or CC breaking, and they make some prediction for the gravitational wave detection. Well, in about how many years you expect you may be able to see some of this kind of gravitational wave generation?
I think my naive understanding is that the LIGO's observation spectrum is a relatively narrow one in comparison with the possible phase space of all the possible phase transition scenarios. So therefore, I think this is always a target to look for phase transition stochastic backgrounds, both in LIGO and in LISA, but it's not really clear when we are detecting these stochastic backgrounds. So another effort, which I think I didn't mention here, which is that I think another band of interest is the frequency band in between the LIGO and LISA band. And in here, I think there were conceptual designs of detectors like the DeSigo detector made by Japanese colleagues, and also the Big Bang Observer detector proposed by people in the US, where they target this band where, relatively speaking, astrophysical backgrounds are more easy to remove, and they might target the stochastic background from inflation. But that depends on the model of inflation and how strong the spectrum can be. But there's a very ambitious plan of searching for that background as well. So yeah, so I personally don't know how long it'll take though. It'll be very exciting to find that.
Thank you. So, there's more questions. See that you don't see more questions. We thank you, Professor Chen, for this very exciting frontier.
Thank you very much.